Let's look at how we can use parametric equations and vectors to model simple projectile motion on Earth. So we're going to start with a recap of acceleration, velocity, and distance. So if we're on Earth, let me draw this actually much smaller. If we're on Earth, we have a constant force of acceleration due to gravity. And measured in feet per seconds, the acceleration on Earth, acceleration versus time, is constant at 32 feet per second squared. So over time, my acceleration stays constant. From this effect of gravity, my velocity over time is going to be linear. It's going to be equal to 32t. For any amount of time that passes, some t, I multiply that by 32t, and that produces my velocity. And so I have my velocity curve that would be something like 32t, and that is measured in feet per second. And then from there, I can actually get to the distance that this results in an object. And so my distance over time is going to be equal to 16t squared feet. And we can again kind of look at, for some time t, my velocity here will be 32t. And because we have a triangle, you have to take half of it, which is where we're getting this 16. And this is a quadratic. So from acceleration, we can go to velocity, to distance. On Earth, the effect of gravity causes a change in position or change in distance of 16t squared. And usually we say negative because that's going down. So let's say I want to model the path of the position of an object. And this object is going to be a projectile. So that means we kind of throw it through the air, or somehow it's going through the air and gravity's allowed to pull it down. And we want to model the position, the path of the position of that object. And we're just going to look at this in 2 dimensions. Obviously, we live in a 3D world, but that's okay. So in 2 dimensions, we're going to look at having an x and y axis. And the x is going to be considered our horizontal, aka the ground on Earth. And the y is going to go to the sky. So we've got x, horizontal ground, y to the sky. And let's imagine we take, let's say we're going to throw a baseball or something. And so there's an initial height that you release the ball at, and then the ball will travel in some sort of parabolic path and eventually hit the ground. And so, we have an initial height of the ball, which we're just going to call y sub 0 or y naught. Why not? And then the ball is going to travel over a bunch of points in space and hit the ground. And it's important to note, this is a position, the x position compared to the y position. We are modeling the position of the ball. Time is the hidden parameter. Time is the parameter, but this is hidden. Nothing about this graph is going to allow you to actually know what the time is. Okay, so if we want to think about what affects the position of an object, and this object is going to be a projectile. Well, number 1 is gravity. And so, let me scroll down. Gravity is going to be, well, let me pause for a second. We're going to measure this position using a vector function, actually. So let's call it the position function of time, and let's say it's a vector function of time, and it'll have a component in the x and a component in the y, and we'll try to figure out what those are. And that might sound a little weird, like how would you use a vector to model a position? But essentially what we do is we just place it at the origin, and for any point or any vector, it can create a point just at the tip of the arrow. So I could have the vector here resulting in this point, then later there's a vector here results in this point, vector here results in this point, so on and so forth. And so all of these vectors eventually just, the tip of each vector eventually traces out our curve. And you'll see why that's kind of nice to use a vector as we go along. Okay, so back to what affects the position. Gravity affects the position. So let's use vectors. So the vector gravity, and let's say the acceleration of gravity. Well, gravity's not accelerating us in the horizontal direction. It's pulling us towards the Earth. So we're going to say that the gravity is 0, negative 32. 0 in the x direction, negative 32 in the y. And it is constant. So the gravity over time doesn't change. So we just write negative 32. Well, we're trying to get to the position vector. We want the position. So the acceleration, right? If we know the acceleration of an object, we can use that to get its velocity. And so from the acceleration of negative 32 feet per second squared, we can say the velocity vector of gravity is going to still be 0, and then it's going to be negative 32 t, because it's changing over time. The velocity is changing constantly based on the acceleration. So every second that goes by, it goes another 32 feet per second. The speed keeps increasing. And then from velocity, we can get to the effect on the position or distance. And so from the velocity vector for gravity, we can actually get the gravity's effect on position. And from the graph above, I mean, 0 still stays 0, but this is actually going to be negative 16t squared. And from physics, you might remember like a 1/2 acceleration times squared kind of formula. That's kind of the same thing happening here. And so this is gravity's effect on the position of the object. And so the position of the object, this can go in to our position vector, because vectors can just all be added together. So the position of my ball over time is affected by the effect due to gravity on position, so 0, negative 16t squared. It's also going to be affected by your throw. So let's say we throw the ball. Let's draw a little hand here. And here's the ball. And your hand accelerates the ball, but then you let go of the ball. So you let go. And there's your hand now. There's your hand now. And here's the ball over here. So you let go of the ball, and now there's no new forces acting on the ball. And so the ball just has a velocity. It's going to have a constant velocity through the air because you let go of it. It maintains its momentum, and it just goes. And let's pretend you throw it so that it's perfectly horizontal. The effect of your velocity is just perfectly horizontal. Your release is perfect. And we have the throw's velocity, which we can treat as a vector. And we're going to say that is constantly, let's say you throw it at 40 feet per second. So the velocity is constant at 40. It's not changing with regard to time. And then we're going to just say the y component of it is 0. From the velocity, if we have a constant velocity, and you might say like, oh, well, why is there no t here? And the reason is because we're saying the velocity is some constant here. So it doesn't matter what t is. Velocity is always 40. It's not changing. But from this velocity, we can go to the effect on position. And now we introduce t, so the throw effect on position is going to be 40t. Because if the velocity is always 40, then the change in distance or the change in position is always 40 times time, 40 feet per second times the number of seconds. And then we're just going to say 0 here. Okay, so now I've got the position, the effect of the throw on the position of the ball. And so I can use the fact that I can just keep adding vectors together. Two vectors add to a new vector. And the throw's position can go in right here. So I can say plus 40t and plus 0. I mean, I could write it, but I don't have to. And so in this situation, I have 40t, and then maybe I have to add the initial height of the ball. And let's say these are the only forces acting on this object. And let's say this height is 5 feet. So I'm just going to say plus 5. And so my position vector, the position of the ball, as a function of time, is going to be equal to 40t for the x, and negative 16t squared plus 5 for the y. So the only thing acting in the y direction is the force of gravity. The only thing acting in the x direction is the velocity you imparted on the ball by throwing it. And so this vector-valued function allows you to get the position of the ball, the xy position of the ball at any time t. And then you can use that to solve whatever you want to know. Let's see here. It really doesn't want to shrink down. All right. Haha. Good. Well, whatever. So say I wanted to know where is the ball at t equals 2 seconds. Well, my x of t, the parametric for the x of t is just going to be 40t. And the y of t is going to be negative 16t squared plus 5. Notice how these are my pair of parametric equations for parameter t, and they're both stored within this vector-valued function. It's all really nice. And it's really nice because I can take other vectors, the gravity's effect on position, the throw's effect on position, add them together, and those created this resultant position vector. So as all these pieces come together really nicely, you just add them, you just break them into their x and the y's. It's very easy and pleasant to work with in this manner. And so for time equals 2, x of 2 is going to equal to 40 times 2 equals 80, and y of 2 is going to equal to negative 16 times 2 squared plus 5. It's negative 16 times 4. So that's actually going to equal to negative 64 plus 5. And that is going to mean that y of 2 is going to equal negative 59 feet. So we better hope this person's standing on like the edge of a cliff or something and is throwing the ball down into the water. Because by not including any vertical component to your throw, our throw is purely horizontal, well, you're only 5 feet off the ground, the ball would actually just go down pretty fast. But usually that's why we're going to have an angle when we throw the ball. Okay, so those are sort of the basics. Let's look at another example. And let's say an archer shoots an arrow. Okay, let's call this example archer arrow. And now we don't have to always put the archer at the starting point on the y-axis, but we kind of just tend to do it. So here's x, here's y. Usually we put our initial position somewhere on the y-axis. So this is like the height they fire the arrow from. Theoretically, you could put the starting point here or anywhere, but usually it ends up just being on the y-axis. So this is y sub 0, the initial height. Let's say they fire it from a height of, I don't know, let's say 4 feet. Okay, so let's let y sub 0 equal 4. Now, the first thing is gravity is still gravity, right? That's kind of delightful. So the acceleration due to gravity is 0, negative 32. The velocity due to gravity is 0, negative 32t. Technically, we could say this is 0t, but what difference does that make? And then the position effect due to gravity is 0t squared and negative 16t squared. This is always the case. So any projectile motion problem that you're building on Earth, this is always going to go into your function, basically, your position function. So if I want to know the position of my arrow, so my position function of time of the arrow, I can always start my equation with negative 16t squared. I can also always start with the initial height, plus 4. And then maybe there's more things that get incorporated there. Now let's say this archer has fired their bow. Let's do a blue bow. And let us say that they fire it such that it's at an angle of theta relative to the horizontal. Okay, so they're firing it somewhere in the air, angle of theta horizontal. The bow imparts velocity onto the arrow because the bow fires, releases the arrow. Now there's no new forces acting on the arrow, so it's just going through time and space with a velocity. So let's say the velocity due to the bow is going to be equal to, or it's going to have some x component, and it's going to have some y component. The velocity to the bow, that x component, right, is going to have the magnitude of the velocity times cosine of the angle theta. From this right here, we basically have theta, there's our velocity, its magnitude, here's theta. So we can break that into components, magnitude of v cos theta, and then our vertical component, our y component, is magnitude of v sine theta. So here we'll have magnitude of v sine theta. And the velocity here is going to be constant. Right, the bow fires the arrow into the air. No new forces are acting due to the bow. The bow is not touching the arrow anymore. So these are both constants. There's no t involved. But then from velocity, we can determine position and the effect on position. And so the position due to the bow, what the bow fired, or the bowstring, or whatever you want to say, the force the bow put into the arrow caused the velocity, which then affects the position. So it's magnitude of v cosine theta times time, and it's magnitude of v sine theta times time. And so those, that's no longer velocity. That is the position, that is the position of the arrow from the velocity. So the position of the bow is given by these. And those can be summed with the position vector from gravity, resulting in the final position of the arrow. And so now I can put magnitude of v cosine theta times time, and I can also put, for the y component, magnitude of v sine of theta times time. Okay. And so as a vector valued function, we are able to just add the velocity from the bow. We're able to add the velocity, acceleration, position from gravity. The position from the bow, and the position from gravity we can combine into the position of the arrow. Those came from the velocity of the bow and the acceleration of gravity. So we can go through these different vectors, add them together at the end. It's really, really nice. And so our function looks like x of t is equal to magnitude of the velocity, cosine theta t, and these are separate. And then our y change, our y position, is given by negative 16t squared plus the magnitude of the velocity sine of theta times time plus 4, which is our initial height. So I'm just going to write y sub 0. And technically, we could also have an x sub 0, although it's rather common that we just start on the y-axis, so that tends to be 0. But this is the general basic case for projectile motion. So the x is going to be given by basically just the velocity, the magnitude of the velocity of the projectile, So if you throw it or hit it off a bat or throw it with a lacrosse stick or shoot a cannon or whatever, the magnitude of that velocity times cosine of the angle you release at times time, and then plus the initial x position, which is usually 0. And then the y component, the y parametric equation here, is going to be gravity's effect. That's always there, negative 16t squared. Then we have magnitude of the velocity times sine of the angle theta that you release at times time, and then plus the initial height. And we tend to have initial heights. But the really nice thing about this all, so that's the basic case, and if you want to sort of memorize this formula and just try to apply it, that's mostly fine to do. But I would like you to see how nice it is that we have the ability to go from velocity to position, from acceleration to velocity to position. Then we can just take these vectors and add them and get the resultant position vector. And one of the really, really nice things about that is it allows us to easily add more forces or considerations. Easily add more forces. So say I wanted to include in this some wind. Say there's a wind and it's blowing, and let's say the wind's blowing kind of in this direction. So I'm trying to fire the arrow this way, wind's blowing this way. So what's that going to do? Well, let's say the velocity of the wind, let's say we have a constant velocity of the wind. Let's say it's blowing at negative 20. It's opposing the direction. It's a pretty strong wind. But let's say it's also going up. It's traveling upward. And let's say it has 10 feet per second. Well, that wind, the velocity of the wind, is going to have an effect on the position. So the effect of the wind on the position is going to give us negative 20t and 10t. And so the really nice thing is, I can just quickly go ahead and add that on into my position of the arrow function, add that onto the position, and I suddenly just added a new constraint, the wind. Oh, and maybe, I don't know, I create a really cool arrow and this arrow has a thruster on it, right? And so I fire an arrow, and let's say, pretend the arrow is just horizontal, and it's got like a thruster. So I'm adding a thrust. And let's say the thruster has acceleration, and we accelerate by 10 in the horizontal direction, constant acceleration. Well, that thruster is going to have an effect on the velocity, and so that will be 10t, and then that thruster is going to have an effect on the position of the arrow, which is going to be given by 5t squared, and then comma 0. And it's great, okay. So now I know what the vector for the position is due to the effect of the thruster on the arrow. And so, I just throw that in for the x and y component here. It doesn't do anything 0 to the y, but it does 5t squared for the x. So now new things are happening. So I can just keep adding things on. Could I add on air resistance if I wanted to have a more realistic model for the real world? Absolutely. And so on and so on and so on. So the basic version of projectile motion is going to be x of t is equal to magnitude of the velocity cosine theta times time, and maybe plus an initial x position. And y of t is going to be equal to negative 16t squared plus magnitude of velocity sine of theta times time plus the initial y component. And because we're using negative 16, this is measured in feet per second, whatever. But all these are feet. And the angle theta is the release angle. So if I have my whatever and I release it like this, and here's the angle theta, here's the magnitude of the vector v, so on and so forth. So these are the really basic equations that you can apply, but it's much more interesting and much more useful in real applications to maybe think about, how do all these vectors combine? How does acceleration lead to velocity to position? Why is it so nice that everything combines and then you can break it down and break it down? So yeah, hopefully that's interesting and useful. And that's simple projectile motion. Very simple, right?